Here we are looking at the slope of a secant and the slope of the tangent. Now, based off of our warm-up, we always had that target point 1, 0, and we noticed that the x's and y value was getting closer and closer to that target point. Well, back from our warm-up continued, we saw that we had y2 minus our target point, which was 2 as that y value, all over our x2 minus the target point's x value. It came out to be 1. But again, our target point doesn't always have to necessarily be 1, 2. So it's really helpful to kind of create a uniformal definition that will work for the slope of any secant. Now let's just let A represent the x value for our target point. Well, when you throw in A into a function, you end up, in other words, that x value for that target point, when you throw that into the function, you end up with some y value, f of A. So this would be our y value for the target point. Well, then when we're looking for the slope of the secant, we have some distance that we are away from our target point. So we end up then with, we'll start off at the bottom, A representing our target point plus whatever distance that we are away from him, represented by that h value that we talked about in the warm-up continued. That would represent our x2 variable. So we have that target value's x value plus some distance that we are away from that. And we are subtracting that by the target values, or target point's x value. In this case, we defined it to be A. On top, we have this y2 value. In other words, that's that point that we are away from our target point. And that's the corresponding y value for that point that we're away from our target point. So then when we throw that into the function, here would be that corresponding x value that we throw into the function. We get that y value that's associated with him, minus our y value when we throw in our target x value. So this is actually the universal secant slope. Now we can actually simplify this up a little bit, where we end up with f of A plus h minus f of A all over. On the bottom, we can see that the a's actually just kind of cancel out, leaving us with just h. This is also known as the difference quotient. So again, this is some point away from our target point based on some distance that we're hoping for, minus our target point from our slopes. And when you simplify things, you end up with the y values, the difference in the y values, all over that difference in the x's that's left over, h. And it's our hope that this h becomes 0, because then we see a truer tangent slope at that particular target point. Now for the slope of the tangent. Now for the slope of the tangent line of a function at some particular point, we'll call this, again, that target point being, the x value being sum A, which again is a constant. Then it's pretty similar actually to our secant. It's pretty similar to this guy. Again, it's pretty much that idea that that h value is approaching 0, where you end up with basically no distance away from your target point. Because again, that's what this actually represents. This h value represents the distance in your x value that's away from our target point of our function f of A plus h minus f of A all over h. So we have to take the limit as h approaches 0 on that, and we're hoping that we're making this guy smaller and smaller and smaller, such then that we actually get to the true slope that is tangent to that line for this particular function at a particular point, at a particular target point. And there is one criteria, though, that is associated with this. The limit does have to exist. So, alright. So again, though, that is the slope of a secant, just kind of an arbitrary secant. And more importantly, though, which led to us the slope of the tangent. So again, this would be equal to our tangent slope. From our 2.1 set of notes.